To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to discuss with you all transformers. Now this is also an application of electromagnetic induction. Now under electromagnetism we have been discussing what electromagnetism is, and thereafter in the previous chapters I discussed what electromagnetic induction is. When there is a conductor placed in a magnetic field, and if there is motion, due to that motion, the magnetic field lines are varied. Because of that magnetic flux, there is an induced electromotive force that gives rise to an induced current. So, based on that, we discussed the two types of dynamo, the normal dynamo and the bicycle dynamo, or the alternating current dynamo and the bicycle dynamo. They function based on the same principle, electromagnetic induction. Only difference is in the alternating current dynamo, the coil rotates, whereas in the bicycle dynamo, the magnet rotates. And also we discussed the moving coil microphone. After that we discussed what alternating and direct currents are. Now I am going to discuss with you all transformers. Now when we say transformers, now you all know a current has voltage and also the magnitude of current, the potential difference and current. Now when we say the household electric circuit, we have discussed this before, the power that is supplied to the household electric circuit. You can remember it is an alternating current with a potential difference of 230 volts, and it is a 50 Hertz alternating current. Now if you look at different devices, now say a current bulb, you might not need 230 volts. For a particular appliance, we might need about 20 volt potential difference, or even less than that. Now you know small bulbs, you can even operate them using 1.5 volts. So like that, we will need smaller potential differences, voltages. The same way you all know, in the hydropower plants or where the power is generated, electricity is generated, the power plants, the electricity generated is increased to very high voltages before they are transmitted, before they are supplied. So usually through the main power supply cable, the electricity that is supplied has a very high potential difference, about 230,000 or 220,000 volts or 220 kilovolts. So that is a very high potential. So from all these, you can understand, students, there is a change. From higher potential difference, you can bring it down. From low potential difference, you can increase the potential difference. So you can basically change the potential difference of a current. That is done by the transformers. Transformers are useful because they allow you to change the voltage of a supply. So very important, because they allow you to change the voltage of a supply. Transformers are used in power packs and in electric appliances such as computers and radios. So in all these, there is a change in voltage supply depending on the requirement of the particular appliance. You need to either increase or decrease the voltage. So here in this diagram, you all can see, students, they have shown a transformer. Now here you can see there are wires, there are coils here and the output. So here what we do is we supply an input and the input is given to the transformer. From that we get an output. So input has a certain voltage, output has a different voltage. The voltage can be either increased or decreased. For that, we use two coils. Here you can see this is one coil. There is another coil there. So there is an input coil and an output coil. Or the input coil is known as the primary coil and the output coil is known as the secondary coil. So if we have the initial one, input or primary coil, then we have the output or secondary coil. So you supply the voltage to the input or the primary coil. There the voltage is changed accordingly and then you get the output through the secondary coil. So that is how a transformer functions. Now that I have explained the basic concept of a transformer, let's go to the lab and have a look at a transformer. Okay students, so like I told you all, I want to show you all a transformer. Now this is a model of a transformer. You can see here, now there is a wire. Initially there is a wire. Now this is to plug in the transformer to our household or the laboratory power supply. And you all know, normally to the household, what is the power supply that we get? We get an alternate current with a frequency of 50 Hz and the voltage is 230 volts. Now look at the wire. Now this wire is connected to this transformer here. Can you see this part? So this particular yellow color box, what you see as the yellow color box is the input coil or what we call as the primary coil. So we supply the voltage to the input coil. Then what we have on top is the secondary coil or the output coil. So if we want to reduce the voltage, can you read it here? It says 6 volts. So when you supply an input voltage of 230 volts, you can get 6 volts as the output voltage. So what type of a transformer is this? We are reducing the voltage. So it's going to be a step-down transformer. So you have two coils, one is the primary coil, the other one is the secondary coil. Now here you can see there are two terminals. If you connect the terminals of a device to these 2 points, you can get the current, you can get the required voltage. Here it's going to be 6 volts and you can operate that particular device. So that's how the transformer works. Now just to have a look at what is inside the transformer, we can remove this and open this part. I can take this off. And we can remove this. Here if I remove the coil, I can show you all how the coil is inside. I can remove the casing. Can you see here? Now this wire is available in different thicknesses and also the different number of turns. So based on that, you all know if we need to reduce the voltage, step down transformer, we need to have more coils in the primary coil or the input coil and less number of turns in the output or the secondary coil. So this is how you get the coils there. Is that okay? So that is the secondary coil that I have taken out. You can see the coils here. The same way, now this is for 6 volts. Like I told you all, 6 volts. Here you can see. Here you can see it is for 6 volts. Then here we have another one for 12 volts. Now here also if I remove this, you can see the coil there. This coil and this coil you can see are somewhat different. So that means depending on how the coil is, you can get different output voltages. So we send the current through this wire, input voltage, and from one of these we can get the output voltage. And since the voltage is being reduced, this will function as the step-down transformer. So this is just for you all to understand how a transformer works. Okay, so that is a model of a transformer. Now I have told you in the previous one of the lessons also, when we discuss electronics, we discussed that about power packs. Now you are familiar with power packs. Most of the electrical appliances, the devices, you get power packs. Inside the power pack also there is a transformer. Now I will show such one power pack to you all. So here you have seen these power packs at home. You all might have used it with different electrical appliances. You would have used it. This is a power pack. Here you can see AC to DC, and also here they give all the specifications. How you will get the output current. So if we try to open this, now this is where you plug it in and the wire connection, everything is shown to you. Now I have already opened it. Here you can see. When we open it, here we have the circuit and this part. You all have to look at this. Now what is this? This is the transformer. Here can you all see the two coils. This is one coil, the red color one is the other coil. Here you all can see. Now this is where we are going to plug in the power pack. So now that from there, the wires are connected to the red color coil. So electricity or current, the voltage will flow in to the red color coil. So what is that? That is the primary coil, because current flows into this first primary coil. From there, we will get the voltage here. So that is going to be the secondary coil. The blue color coil will be the secondary coil. So that is again connected to the wire here. You can see from here there is connection to the board, and here you can see the connecting wires. Now this part will be inserted into the device. So here you can insert this into the device. So that's going to be the output voltage. So this part here is the transformer. And here you all can remember, students, although we get 230 volt current, the current used by the device will be less voltage. So that is also going to be a step down transformer. So inside the power pack also we get the transformers. This is for you all to understand that, or to know that there are transformers used in the power pack also. So with that, students, we looked at the structure of a transformer, and this is how you get a transformer in a power pack. I'm sure you all can understand how a transformer helps us in our day-to-day activities. Okay, students. So you all saw the coils in the transformer. So you do have an idea as to what the transformer is. So now we'll try to understand how the transformer functions. So for that, I'll move on to the next slide where we discuss an activity. So here, activity, explore the function of a transformer. For that, these are the apparatus that are required to us. So here we need an insulated copper wire. Then we need iron wires, that is soft iron wires. Instead of the soft iron core, we use the soft iron wires, but these are like small strips of wire or very thin rods. They are bundled together. So here I'll say bundle of soft iron wires. Then we need the battery. Then we need the galvanometer. And we need a switch. So this is what we will do. We have this bundle of soft iron wires. Around that, we will make one coil of insulated copper wire, which is connected to the battery and a switch. We leave a space and then we make another coil that is connected to the galvanometer. I will explain that in the next slide with the diagram. So here you can see, this is what I told you all. Now here, these are the bundle of soft iron wires. So here, that is this in the middle, here you can see. Then here you can see the wire coil made from copper wire, insulated copper wire. So you connect the switch, the batteries, and the copper wire is coiled around it. Then there is a space. Then we make another coil that is connected to the galvanometer. Now the galvanometer, you all know, indicates the current flow as well as the direction of the current flow. So that is why we use the galvanometer. So that's how we connect it. Now let's say, wrap about 100 turns of insulated copper wire around the bundle of soft iron wires. So here it is the insulated copper wire, and around that is wrapped around the bundle of soft iron wires in order to form a coil as shown in the figure. Is that clear? Now form another similar coil on the same soft iron wire rope at about a distance of 1 centimeter from the first. So there should be a distance. They should not be touching each other. They should not be in contact with each other. Connect a switch and two 1.5 volt dry cells in series to one of the two coils above. Connect the other coil to a center zero galvanometer. So all what I explained. Now observe the deflection of the galvanometer by turning the switches on and off, and fill the table given below by crossing off the incorrect words. So what we do is we switch it on, observe the galvanometer. Keep it on, observe the galvanometer. Switch off, observe the galvanometer. We can repeat it a few times to understand what really happens. So you have to see as you switch on what happens, and when you keep it on continuously what happens, as you switch off what happens, and if it is off continuously, the change. So those are the instances where you need to observe the galvanometer. So that again is a simple procedure where you make a bundle of soft iron wires. Around that you wrap a coil of insulated copper wire connected to the switch and batteries. Then there should be a space about 1 centimeter. Then you have the second wire coil, that is again copper wire coil, around the soft iron wires that is connected to the galvanometer. So here you can see the two letters AB, that is to identify the direction of current flow, A to B or B to A. Is that clear, students? So now that you know the procedure, we will go to the lab and do the activity. Okay, students. So now I am going to do this activity in order to understand the function of a transformer. So to do the activity, I have all these materials here. I have already connected them in the correct order. So here you can see this is a galvanometer, a center zero galvanometer. So you all know we can look at the deflection. It can deflect this way or this way. So that shows the direction of the current flow. And here you can see the galvanometer is connected to this part. If you look at this closely. Now these wires, those are soft iron wires. I have a bundle of soft iron wires here. And here you can see this side is connected to the copper wire here. This side is connected, and on this side the other copper wire is connected to a switch. And from the switch here you can see I have 4 dry cells. If we take 2 dry cells also it is okay, but in order to observe the deflection more clearly, I have used 4 dry cells here. So then it is a complete circuit. And also I have this table that is given in your textbook. You can see here when we turn on the switch, when you keep the switch turned on continuously, when you turn off the switch, and also when you keep the switch turned off continuously. In all these instances, what we need to do is you need to observe the galvanometer. You have to observe it clearly and see whether there is a deflection in the galvanometer, and if there is a deflection, in which direction. Whether it's going in the clockwise direction or the anti-clockwise, that is positive or negative current. All that has to be observed clearly. So first what I will do is, I will show you all what happens so that you can get the observation clearly, and then we will fill this table. Actually, when we say fill this table, all the terms are given to us. Galvanometer deflection deflects to the right or left. So you have to observe whether it's to the right or left, and then we have to cut off the unwanted word. We have to leave the correct word there. So first we will try it once. Now observe when I close the switch, observe the galvanometer. So now I'm going to do the activity. We will get this a little bit closer so that you all can observe the change. Now I have the switch and the galvanometer. You can see the coil is also here. So you have to observe what happens when I close the switch. So now I'm going to close the switch. Observe. Now did you all see a deflection there? I'll do it again. As I close the switch, you have to look at the galvanometer. As I close the switch. Did you all see a deflection there? Now again, if I repeat, you can see as I close, there is a deflection in the positive direction. But now I have the switch closed continuously. Is there any change? No. The galvanometer remains at 0. Let's open the switch now. What did you see there? I'll close it and open it again. When I open, you can see there is a deflection in the negative direction. As I open, there's a deflection. But now is there a change? No. So you can see clearly when we close the switch and open the switch. When I do that action, you can see a deflection in the galvanometer. So when I close, there's a deflection. There you see, when I close it, there was a deflection in the positive direction. Now when I open, there is a deflection in the negative direction. But if it remains closed or remains open, there is no deflection. That is what you all have to understand. So this is the observation that needs to be filled up in the table. If you look at it here, now when the switch is turned on, what happens to the galvanometer deflection? Now this side, I will take it as the right deflection. Now for you all also, this way is right. So deflects to the right. Deflects to the right. Then what happens? So that means there is a current flow in the second circuit from A to B. So the second conclusion, if you look at it, a current flows in the second circuit from A to B or B to A. If you compare this with your diagram, students, you all can see this side is A, this side is B in the diagram given in your textbook. So current flows from in this direction. So there we can take it as A to B. So I will cut the first part of B to A. So there is a deflection to the right and current flows from B to A. Then, if I keep it turned on continuously, is there a deflection? No. There is no deflection. So that means current does not flow in through the coil. And when it is turned off, what happens? Deflects in the opposite direction. So earlier it was to the right this way, now it is to the left. To the left. And also a current flows or does not flow. Current flows in the opposite direction. So you were able to see that current flows from B to A. And turned off continuously, again there is no deflection and current does not flow. So those were the observations. I will repeat this again once more So you can observe it more clearly. Now the switch is turned off. So as you can see, all the components are connected together, and you have to understand there is the soft iron cores. These are the soft iron wires, and here it is the copper wire coils. And as I turn on the switch, now I will close the switch. You can see there was a deflection in the positive direction. And now when it is continuously turned on, there's no deflection. If we open it, there is deflection in the opposite direction. And when it is continuously turned off also, there is no deflection. So that is what you need to understand, students. So what happens here? Now we have the batteries, the dry cells here, that is connected to this wire coil. And when I close the switch, the circuit is complete. Current flows through the copper wire. Due to the current flow, there is an electromagnetic induction taking place. A magnetic field is induced. Because of that magnetic field, there is a magnetic field induced in the second coil as well. So due to that, there will be an electromotive force that will generate an electricity flow through the second coil. So that is what we read in the galvanometer. Can you all understand that? So we are providing current through the first coil. Because of that, a magnetic field is induced, and that generates a magnetic field in the second coil where there is electricity generated. So that is what we observe here, the current. And this depends on the change in magnetic field. That is why when you close, as you close the switch and as you open the switch, we see a deflection here. But when it is continuously, the current is flowing, there is no deflection. That is what you need to understand. So in a transformer, this is the function of a transformer. Now this is the coil where you give the input current. And this is the coil where you will be getting the output current. So you give a certain amount of input current and you will get a certain amount of output current. We will be transforming the current, either increasing the current or decreasing the current. So that is how a transformer functions. Okay, students. So did you all see the observations clearly? I'm sure you all did. So what did you all observe? As I turn on the switch, that is as I close the switch, you were able to see the deflection in the galvanometer. And the galvanometer deflects towards the right side. So you all know that the current flows in the direction A to B. But when I keep the switch closed continuously for some time, you saw that there was no deflection in the galvanometer. That means there is no current flow in the second coil. Then again, as I turn off the switch, again you were able to see a deflection in the galvanometer. That was in the opposite direction. That was towards the left. And at the same time, you all know that the current flows in the opposite direction, that is B to A. Thereafter, when we keep the switch turned off continuously, then also there was no change in the galvanometer. There is no deflection. That means there is no current flow. So those were the observations. First I will write them here. Here you can see switch is turned on, galvanometer deflection and conclusion from that. So when it is turned on, deflection or deflects to the right. From that, what did we conclude? You can remember I had the table that was given in your textbook. So there you can remember current flows from A to B. So current flows from A to B. Then, when you keep the switch turned on continuously, what happens there? There is no deflection, no current flow. Then, so when it is turned off, as we turn off, again you see a deflection, deflects to the left. So what was the conclusion we get from there? We can say current flows in the opposite direction, or I can say current flows from B to A. Current flows from B to A. So that is as we turn off the switch. Then if I have the switch turned off continuously, there was no deflection. So there again no deflection and no current flow. So this is what you need to understand from here, students. Now initially you had one coil. There was a distance between the first coil and the second coil, and the second coil was only connected to the galvanometer. So there was no power supply to the second coil. So that means unless there is an induced magnetic field and an induced current, there will be no deflection in the galvanometer. But we supply current to the first coil. You can remember that. In the activity, if we check that, you can remember the first coil is connected to the batteries, whereas the second coil is connected to the galvanometer. So as I turn on the switch, there is current flowing through the first coil. So because of that, there is a magnetic field induced in the first coil. That induces another magnetic field in the second coil, which again induces a current flow. Due to that current flow only, you see the deflection in the galvanometer. So you know there is current flow in a certain direction. But when you keep the switch turned on continuously, what happens is there is current flow in the first coil, but the thing is the current flow is continuous. So because of that, there is no magnetic flux. Because of that, there is no induced magnetic field in the second coil. That is the difference, students. You all have to understand. As you turn on, there is a difference in the magnetic field lines in the first coil as well as the second coil, which induces an electromotive force that makes the current to flow. But if you keep the switch turned on continuously, there is no variation in the magnetic field lines. So because of that, there is no electromotive force induced in the second coil. Therefore, you do not see a deflection. That means there is no current flow. But in the next step, as I turn off the switch, again there is no current supply to the first coil. Because of that, the magnetic field in the first coil changes. Therefore, there is a variation in the magnetic field of the second coil, and that gives rise to an induced electromotive force which makes a current to flow. That is why you see a deflection, but this deflection is in the opposite direction. That's also important. Initially deflects to the right, then it deflects to the left. So when you turn on right direction, turn off, it's towards the left. So they are in opposite directions. That's very important. The deflection will be in opposite directions when you turn on and turn off the switch. So because of that, current flows from B to A. That is what happens in the activity. Thereafter, if we have the switch turned off continuously, again there is no magnetic field in the first coil. The same way, there is no magnetic field in the second coil. Because of that, there is no deflection, there is no current flow. So this phenomenon, where when you supply current to the first coil, there is induced magnetic field lines that induces a magnetic field in the second coil, and from there is an induced electromotive force that is leading to the current flow. This particular concept is based on electromagnetic induction, and this particular function where you have two coils and the magnetic field change in the first coil induces a magnetic field in the second coil, which gives rise to the flow of current, is used in the working of a transformer. We will be discussing that after we discuss the conclusions of this activity in the next slide. So here, these are the conclusions that we already discussed. You will be able to draw the following conclusions from the above activity. A current is induced in the second circuit at the instant that a current starts to flow in the first circuit. As the current starts to flow. So here, induced at the instant that a current starts to flow in the first circuit. When the current in the first circuit is flowing continuously, current in the second circuit ceases to flow. So that was the second conclusion. At the instant that the current flow through the first circuit is turned off, a current is induced in the second circuit in the direction opposite to the direction of current flow before. So that is also what we understood. So here current flow in the opposite direction. And when the current flow in the first circuit ceases, the induced current in the second circuit becomes 0. So all the conclusions that we understood. As the current starts to flow, there is an induced current in the second circuit. As the current is stopped, again there is an induced current in the second circuit, but in the opposite direction. But continuous current flow, there is no current in the second circuit. At the same time, when there is no current flow continuously in the first circuit also, there is no current flow in the second circuit. That is the basic principle of a transformer. Is that clear, student? So then, I'll move on to the next slide. In this activity, there is no magnetic field through the coils before a current passes through the first coil. So initially, we only have the bundle of soft iron wires, around that the copper wire coil. So there is no magnet. We did not have any magnets, no magnetic poles, so there is no magnetic field. That means, what happens? A magnetic field is generated when a current begins to flow through the first coil. So that is important. A magnetic field is generated when a current begins to flow through the first coil. This magnetic field also passes across the second coil through the soft iron wires. As a result of this change in the magnetic field through the second coil, an electromotive force is induced. So there an electromotive force is induced in it, which causes a current to flow through the galvanometer, giving rise to a deflection in the galvanometer. This is also something we discussed. So initially in the primary coil there is no magnetic field, but as we supply current there is magnetic field induced. That induces a change in the magnetic field of the second coil. And there, due to the magnetic field, there is a current flow. That gives rise to the deflection in the galvanometer. When a current is continuously flowing through the first circuit. So here, when a current is continuously flowing through the first circuit, the magnetic field remains constant. I told you all this. And there is no variation in the magnetic field through the second coil. Therefore, an electromotive force is not induced in it. Then the galvanometer deflection is 0. So, these are the observations. Now here, this is what you saw in the first And the third observation, as you switch on and switch off. But when you have it turned on continuously or turned off continuously, then there is no deflection in the galvanometer. So those are the explanation. As you turn on, as you turn off. Keep it turned on continuously, keep it turned off continuously. So when there is a change in the magnetic field, there is an induced current. When there is no change in the magnetic field, there is no induced current. Is that clear? And also, you can understand the direction of the movement, deflection changes. That means you need to supply a varying current. As you turn on and turn off, the direction of the induced magnetic field and the induced electromotive force are changing. That means for a transformer to function, we need to supply alternating current. So with that, I'll move on to the next slide. When the switch in the first circuit is open, the current flow is terminated. The magnetic field caused by the current diminishes together with the current. As a result of the diminished magnetic field, the magnetic field through the second coil changes and therefore an electromotive force is induced in the second coil. This induced electromotive force has a direction opposite to that of the previous occasion. So this is what I told you. When you compare the first and the third instances. Therefore, the galvanometer deflection occurs in the opposite direction. When there is no current flow through the first coil, an electromotive force is not induced in the second coil, as there is no variation in the magnetic field. Therefore, the galvanometer deflection is 0. Therefore, we can conclude that an electromotive force is induced in the second coil whenever there is a change caused by the first coil in the magnetic field through the second coil. That's very important. An electromotive force is induced in the second coil whenever there is a change caused by the first coil in the magnetic field through the second coil. So, only when there is a change. Otherwise, there is no induced electromotive force. Is that clear? So, with that, I'll move on to the next slide. If we connect an alternating voltage to the first coil instead of a battery, then as the magnetic field varies continuously, a similar alternating voltage difference is induced in the second coil too. So, like I told you, now these functions more better or based on alternating current because the changes are observed when you on and off the switch. So, instead of a direct current supply, if we connect an alternating voltage to the first coil, then of course an alternating voltage difference is induced in the second coil. Such a combination of coils linked by a magnetic field is known as a transformer. So here, combination of coils linked by a magnetic field is known as a transformer. So you need to have two coils, the primary coil and a secondary coil. Transformers only work with AC currents. Transformers only work with AC currents and AC voltages. They will not work with DC currents, that is direct currents and direct current voltages. Transformers work with alternating currents or voltages and with changing direct currents only. So, in the activity, we had changing direct current. We switch on, switch off. So, that is a changing direct current, or else with an alternating current or alternating voltage. So, they do not work with this. There is a mistake in the textbook, students. This should be They do not work with continuous, or you can say constant direct currents. They do not work with continuous or constant direct currents. If you supply the direct current continuously, they don't work. If it is an alternating current or voltage or changing direct currents, then it works. If the direct current is continuous, then the transformer does not work. So then, the figure below shows the symbol used to represent a transformer in the circuit diagrams. So here you can see this is the symbol. Now here you can see initially you see a coil. So this is to represent the primary or input coil. The first coil in the activity where you connect the switch and the battery. So here only you supply the input voltage or the input current. Then we have 3 lines. They actually represent the soft iron wires, or we can use a soft iron core. In the symbol, students, you don't have to mark what they are. I'm just explaining the meaning. Why they have a coil that represents the primary coil. Then the 3 lines represent the soft iron wires. And this coil, the second coil, you saw the second coil also in the activity. So that is the output or secondary coil. So this is the output or the secondary coil. So what we did in the activity, the components that are needed for a particular transformer. The primary or the input coil, soft iron wires, and the output or secondary coil. So here you can see the straight lines between the 2 coils represent the soft iron core. Soft iron wires or soft iron core. So that is the symbol of a transformer. Then I told you all, the transformer changes the voltage. So it can either increase the voltage or decrease the voltage. If it increases the voltage, then we call it the step-up transformer. If it decreases the voltage, we call it the step-down transformer. Increasing the voltage, step-up transformer. Decreasing the voltage, step-down transformer. So how do we do that? By changing the number of coils in the primary and secondary coils, or the input and output coils. That is what I am going to discuss after this. So with that, if I move on, construction of a transformer. Now here, figure shows a simple arrangement of a transformer. It has 2 insulated copper coils wrapped around a soft iron ring. So here you can see, students, this is a soft iron ring, or you can call it a soft iron core. In the first activity, we used a bundle of soft iron wires. Then you have the primary coil. Primary or input coil. And here you have the secondary or output coil. Then here you can see this is an alternating AC current source. So maybe a bicycle dynamo. A dynamo can be connected there, AC current source, so alternating current. You supply the alternating current to the primary coil, there will be a magnetic field induced. Due to that magnetic field, there will be another magnetic field induced in the secondary coil. Due to that, there will be an electromotive force induced, and that will give rise to an induced current flow, which will flow through this resistor. This is a resistor or what we can call as a load. A resistor or a load. Is that clear, student? So, resistor or a load. Let's say we connect it to a certain device. Now, we said these transformers are there in a laptop. The laptop charger, the power pack that is connected to a laptop. So, the laptop will be the load because you are supplying the current to that. So, you get the input current from the main household power supply. That will be the alternating input current. That will pass through the transformer and there you will connect it to the load or the resistor or the particular device. So, in this particular one, we have the primary coil and we have the secondary coil. Now, I said depending on the number of turns in the primary coil and the secondary coil, we have the step-up transformer and the step-down transformer. So, to do that, we need to know the number of turns. So, the voltage that is supplied to the primary coil, that is known as Vp. If I fill this table here, so like I said, if I fill the table, the number of turns in this coil is termed as Np. Number of turns Np. Number of turns is indicated by N and the P as the subscript indicates the primary coil. The same way in the secondary coil. Number of turns is indicated as Ns. Number of turns in the secondary coil. The same way, the potential difference that is applied to the primary coil is indicated as Vp or electromotive force. Electromotive force V primary. That is, to the primary coil, the electromotive force that is applied is denoted as Vp. Voltage primary. The same way, electromotive force Vs. V secondary. So, based on this, we can have the two types of transformer. To increase the voltage, then what we can have is, if we have, let's say, number of turns, secondary. So, if we have, let's say, 10 turns here and if we have 100 turns there, that is, number of turns in the primary coil is 10 turns, number of turns in the secondary coil is 100 turns. So, you all know the induced electromotive force depends on the number of turns. It is directly proportional. So, when the number of turns increases, the induced electromotive force will increase. So, what will happen is, if you supply a voltage to the primary coil, let's say we supply 3 volt supply, 3 volt. Voltage is 3 volts. Then in the secondary coil, you will get increased voltage. Since the ratio between the number of turns is 10:100, that is 1:10, the same way the potential difference will be increased. So, when you have 3 volts here, you will get 30 volts there. So, that will be how the step-up transformer functions, increasing the voltage. So, this is known as the step-up transformer. So to denote the step-up transformer, what we do is we show the coil, but here more coils there. Now the primary coil has less turns, secondary coil has more turn. So here this is N primary 10, N secondary 100. You don't have to count and draw, but from the symbol you know it is a step-up transformer. Is that clear, student? The same way, to decrease the voltage, there what happens is, again we have the primary coil and the secondary coil. So let's say if we have in the primary coil NP is equal to, let's say, 200 turns. Then in the secondary one, we need to have less. Let's say we have only 100 turns. So more turns in the primary coil, less turns in the secondary coil. Number of turns is proportional to the electromotive force. So here the electromotive force will be high, here the electromotive force will be less. So let's say we supply Vp. We'll say 4 volts. Now here the ratio is 200 is to 100. Then of course you will get 2 volts according to the ratio. So this is known as a step-down transformer. A step-down transformer. So how do we represent a step-down transformer? Primary coil has more turns, secondary coil has less turns. You need to show the soft iron wires, then the primary coil with more turns and the secondary coil with less turns. So you can see that. That is a step-down transformer. Is that clear, students? So from these, now here, if I go back, you can understand we have the 2 coils, the number of turns in the primary, number of turns in the secondary. Electromotive force is in the primary coil, electromotive force in the secondary coil. So to increase the voltage, what do? We have less turns in the primary coil, more turns in the secondary coil. So this is the symbol for a step-up transformer. So here, like I explained to you all, the ratio between the number of turns gives the ratio between the voltage difference. So when the number of turns increases 10 times, the voltage also increases 10 times. The same way, to decrease the voltage, what do? We have the primary or the input coil, secondary or the output coil. There in the primary coil we have more turns, in the secondary coil we have less turns. So then it is a step-down transformer. Now here 200 turns, 100 turns. Ratio is 2:1. The same way, input potential 4 volts, output potential 2 volts. The ratio again is 2:1. So from that, if we try to come up with the equation or the equation that is used to determine the output voltage, that can be given this way. So that can be written as number of turns in the primary coil divided by number of turns in the secondary coil. That is equal to potential difference in the primary coil divided by potential difference in the secondary coil. So, potential difference in the primary coil divided by potential difference in the secondary coil. So, that is how we can get it. If we use the symbols for this. Now, number of turns in the primary coil, we use the symbol NP. Number of turns in the secondary coil, NS. That is equal to potential difference or the electromotive force in the primary coil, Vp, divided by Vs. That is the potential difference in the secondary coil. So, Np over Ns gives you Vp over Vs. So, this is an equation that you need to remember, students. You all have to keep this in mind to do calculations. Now, for the two examples that I showed you all, if I go back, now here I explained to you all the increase in voltage. You can see number of turns is given to you and the potential difference is given to you. If we use the equation, now let's say Np over Ns equals Vp over Vs. So, there. If I do the calculation, primary 10 turns and secondary 100 turns. Primary voltage 3 volts, secondary voltage 30 volts. Now, you get the ratio, no? 10 over 100, 1 over 10. The same way, 3 over 30, 1 over 10. So, this is how it works. So, if you didn't know what the output voltage would be, you can use the equation to find that voltage. You can look at the turns, from that you can predict, you can understand, or else we can use this equation. Is that clear? The same thing, if we apply to the step-down transformer. Here, let's say we don't know the voltage that would be obtained from the secondary coil. Then what do? We use the equation N primary over N secondary equals V primary over V secondary. So, N primary 200 turns, secondary 100 turns. Voltage supplied is 4 volts. We don't know the voltage in the secondary coil. If you rearrange, voltage in the secondary coil will be 4 into 100 divided by 200. So, when you simplify, you will get it as 2 volts. 100, this and this, 1 over 2, 2 and 4, 2. So, you will get the value as 2 volts. So, in case you need to find out, you do it this way. For that only we have the equation. So, that is how the transformers function. I am sure you all can understand that. So, with that, students, I will move on to the next slide. So, here you can see normally one coil of a transformer is connected to an alternating power supply, while the other is connected to a load or a resistor or an electric appliance operated with an alternating power supply. So that is all what we discussed before. The first coil that supplies power to the transformer is known as the primary coil or input. The second coil from which power is taken out of the transformer is known as the secondary coil or the output. The voltage supplied to the primary is denoted by Vp. Voltage supplied to the primary is denoted by Vp, and the voltage given by the secondary is denoted as Vs. So these are all what we already discussed. So I'm sure you can understand that. Then the alternating voltage Vp applied to the primary gives rise to an alternating current flow in the primary circuit, which in turn gives rise to an alternating magnetic field. So we have understood this. This alternating magnetic field is linked to the secondary coil by the soft iron core, and this varying magnetic field induces an alternating voltage, that is Vs, in the secondary coil. That is the function of the transformer. The relation between the voltages and the number of turns of a transformer can be expressed as follows. I gave you the equation before also. If we rewrite that, number of turns in the primary coil divided by number of turns in the secondary coil. That is equal to, so here, voltage difference in the primary coil divided by voltage difference in the secondary coil. So from that we got the equation N primary over N secondary is equal to V primary over V secondary. So this is the equation. I told you all that is important. This is given in words, this is given in symbols. Number of turns in the primary coil divided by the number of turns in the secondary coil, that is equal to voltage difference in the primary coil, voltage difference in the secondary coil. You have to understand that. Using this, we will be doing calculations. So I will move on to the next slide. According to this relationship, by varying the ratio between the number of turns Np in the primary and the number of turns Ns in the secondary, and output voltage larger than or smaller than the input voltage can be obtained. So that is how we get the step up and step down transformers. So step up transformer and step down transformer. So we have two types of transformers based on whether the potential difference is increased, output voltage is larger or smaller than the input voltage. I'm sure you all can understand that. With that, I'll move on to the next slide. So here we have the step up transformers and step down transformers. So already I showed you all the symbol. Now look at this. Here you know it is the alternating current source. This is alternate current source, maybe a bicycle dynamo. Then we have the primary coil. Look at the number of turns. You can see there are only 3 turns. Then The two lines, they indicate the soft iron core. Then here you can see secondary coil has lot of turns. So what is this? It will be a step-up transformer. Here you can see secondary coil, and here you can see the load or the resistor or the device. So then, transformers that give an output voltage larger than the input voltages are called step-up transformers. So here, transformers that give an output voltage larger than the input voltage are called step-up transformers. They have a larger number of turns in the secondary coil than in the primary coil. They have more turns in the secondary coil than the primary coil. So you are familiar with this. Then I'll move on to the next one. Here again we have step up and step down transformers. Again look at the diagram. You can see this is alternate current. Then this is the load. You see the symbol of the transformer, primary coil, secondary coil. You can immediately identify. There are a lot of turns, only 3 turns there. So you know it has to be a step down transformer. This is a step down transformer. Transformers that give an output voltage smaller than the input voltage are called step down transformers. So input voltage is high, output voltage is less. So step down, reducing the voltage. Step down transformers. And also they have smaller number of turns in the secondary coil than that in the primary coil. So I am sure you all can understand these two. So that is the step up and step down transformer. I have introduced what they are. I showed you all an example as well. Now with that students, I am going to end this chapter. And as I start the next chapter also, I'll be discussing where we use this step up and step down transformers, and we will do calculations related to the transformers.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.